Moving forward with chapter 6 of this book called Physical Oceanography and Climate. Remember that I'm just providing very brief podcasts as an addition to the course I already have on Introduction to Climate Science, Modern Climate Change, Climate Modeling, and so on. So definitely read the book if you want to get the full evolution of the course as seen by Chris Kranauskas in his book. Okay, so always remember that. We are going to first look at the steady state response and then come back to some transient wind forced responses just to prepare ourselves. The key concept again here turns out to be the western boundary intensification and some special features like inertial motion and Kelvin and Rossby waves and so on. So we already looked at the governing equations, F equal ma, Newton's law of motion for the ocean, also for the atmosphere. We had written it as zonal and meridional equations with acceleration term, pressure gradient term, Coriolis term, horizontal and vertical eddy momentum mixing or viscosity. Actually, I should be careful. Viscosity terms, and of course the momentum advection term v dot grad u. And similarly, you have the this is a little bit misleading in the sense this should be written as a scalar as well because we are in the zonal direction, but nonetheless it will be u du dx, v du dy, and w du dz. So the x part of it and the meridional part of it here. We looked at earlier the balances of various types where we just looked at geostrophic balance of pressure gradients and Coriolis term, or acceleration balanced by pressure gradient and so on. But obviously when you have wind forcing and the ocean's response, you cannot ignore Coriolis. So you can start with the simplest case where, let's say, there is wind blowing at the surface given by the term on the right here, 1 over rho d tau x dz. Of course, rho is the density of ocean water, and d tau x dz is how the wind stress is distributed in the ocean. And that should, if there are no other terms, it's a steady flow and only the wind forcing is creating motion and there is no other friction, then obviously the zonal wind stress will, because of Coriolis, give us a meridional velocity, and meridional wind stress will give us a zonal velocity when we balance Coriolis with wind forcing. This is kind of what was done by Fridtjof Nansen and his graduate student Walfrid Ekman. The story goes that Nansen, who tried to go to the North Pole, got stuck in the ice and his ship got crushed, so he went back with a reinforced ship, but he noticed that the icebergs drifted at an angle to the direction of the wind. There is a chopper going by here, so let me stop for a second as it passes by. So Nansen came back and asked his graduate student to figure it out, and Nansen had already qualitatively figured out the Coriolis and the impacts of wind forcing on the circulation and so on, and Walfrid Ekman put some equations behind them. So if we just integrate these equations, of course velocities or currents are this average speed with which the water parcel is moving, but if we integrate it over an area or a volume, we get the transport, or across an area we get a transport. So when you integrate let's say down to the bottom of the frictional layer where the wind vanishes, so at the surface winds are coming in, they are going to be slowly penetrating momentum and momentum budget that we looked at before, at some depth the winds are not felt anymore. So if you integrate over that depth without saying exactly what that depth is, then you end up with zonal Ekman transport, which is related to meridional wind stress and the Coriolis, and meridional Ekman transport, so over the Ekman layer, is minus tau x over rho f, so it's related to zonal wind stress. So the bird's eye view and 3D views of the Ekman spiral beneath a steady northward wind stress shown here, and that's the medium gray line here, and a reinterpretation of just the top two vectors shown here. So what is happening if we look at the Ekman spiral just from the top, you will see that the wind stress is blowing towards the north, so northward wind stress or southerly wind, and the surface transcurrents will go to the right of the wind stress because of Coriolis, and then that surface layer which is being dragged by the wind stress will drag the water below it. So the friction felt by the layer below is from the ocean currents, so that's going to be to the right of the surface currents, and then that will drag the layer below and so on. So in 3D you will see that that's the northward or y direction, this is the zonal direction, this is the z direction, and you have northward wind stress producing a tilted currents to the right of the wind stress. That current is dragging the layer below to the right of it, and the layer below to the right of it, and so on. So at some point the water will in fact be moving opposite to the direction in which wind is moving. So this is like a spiral going down, which is called the Ekman spiral. Sorry, I have a dry throat here. Right, so if we integrate the currents over this depth, then you get Ekman transport, wind-driven transport, which is at right angle to the direction of the winds. Nansen had also used a drag, so you have winds in this direction, and there is the Coriolis acting to the right of the velocity, which is to the right of the winds themselves, and of course the drag would act opposite to the direction of motion, and the layer below at, let's say, 0.1 z Ekman will be directed in the direction of a velocity here in terms of the forcing, and the velocity below will be directed to the right of that forcing from the top, frictional drag that's pulling, which is what we have put here. So that will be to the right of that, and then drag will act opposite to that, and then Coriolis will act to the right of that, and so on and so forth. So you end up with Ekman transport, which is very easily seen as just in this steady state response as related to wind stress and the Coriolis. Obviously you will see immediately that F goes to 0 at the equator, so you will have trouble with Ekman velocities on the equator. But now, remembering ocean is incompressible, we can go back to our continuity equation, which was just divergence equal to 0. So du dx plus dv dy plus dw dz was 0, so we can write minus dw dz equal to horizontal divergence, which allows us to relate our vertical Ekman velocity to the Ekman transports we just derived in a very simple way, and write it as d dx of u Ekman plus d dy of v Ekman, because we have assumed a steady state with just wind forcing balancing the transports, and that gives us the relation that Ekman pumping or Ekman velocity is just 1 over rho f times del tau y del x minus del tau x del y, and we know from before that this is just the curl of the wind stress. So if you curl your fingers around the winds, you will get the curl direction of the net curl of the wind stress. So W Ekman is curl tau divided by rho F. Very, very simple relation, right? So obviously you can see that even though F goes to 0 on the equator, we have cold temperatures here being brought up, and we already mentioned upwelling happening on the equator, and that's related to divergence. So the wind forcing pushes the water away from the equator, north of the equator, because of Coriolis pushing to the north, to the right, and to the left here in the southern hemisphere. So water is being pushed away from the equator, so you still have upwelling. It's just that Ekman pumping is not, Ekman velocity is not defined on the equator by this definition. So the dynamic upwelling versus Ekman pumping has to be carefully differentiated. I keep saying Ekman pumping because when we say Ekman pumping, it is what the wind stress curl does in terms of pumping water down, whereas Ekman suction is when there is a curl going the other way and waters are pulled up. So that's Ekman suction. Upwelling is typically Ekman suction, even though here it's Ekman divergence, so water being diverged by the Ekman currents and Ekman transport going away from the equator. Of course, typically in the subtropical gyres, we will see in a minute, we have Ekman pumping, so convergence and downward pushing of the water. So you can see that here clearly. So Ekman pumping and upwelling and dynamic divergence driven upwelling is producing mean dynamic topography to be lower here, in the range of 40 to 50 centimeters with respect to let's say the geoid or the flat sea level surface. And as you go towards the subtropical gyres, obviously westerly winds and northeasterly trades are together producing a convergence, and if you look at the wind stress curl by curling your fingers around the westerlies in the mid latitude and northeasterlies in the lower latitudes, you get thumb going into the ocean, which means there is downward Ekman transport, Ekman pumping, Ekman velocity is downward, so you get piling up of the water and dynamic height that is high here. Similarly in the subtropical gyre here. Of course in the subpolar gyre you get Ekman suction, so the dynamic height is low, negative here with respect to the mean sea level. Okay, keep that in mind, and we'll come back and look at the further details on how wind stress curl and Ekman velocity, Ekman transport, Ekman pumping, Ekman suction, and so on work together. And of course the big difference between the atmosphere and the ocean we will see is that oceans have boundaries, and wind forcing, especially the dependence of Coriolis on latitude, makes a big difference in how the ocean response to wind forcing gets set up. Okay.